Hello everyone. In this presentation, I will give a brief introduction to our work for CVP or 2025 Submission Learning Occlusion-Robust Vision Transformers for real-time UAV tracking. UAVs are leveraged in a plethora of applications, with increasing emphasis on UAV tracking. This form of tracking poses an exclusive set of challenges such as tricky viewing angles, motion blur, severe occlusions, low resolution, and the need for efficiency due to UAV's restricted battery life and computational resources. In this paper, we present OR-Track, designed to enhance the occlusion robustness of VIT-based UAV trackers by learning feature representations that remain reliable even under target occlusion. Specifically, we propose to learn occlusion-robust representations, ORR, based on VIT for UAV tracking by enforcing an invariance of the feature representation of a target with respect to random masking operations, modeled by a spatial Cox process. Hopefully, this random masking approximately simulates target occlusions, thereby enabling us to learn VITs that are robust to target occlusion for UAV tracking. Additionally, to facilitate real-time applications, we propose an adaptive feature-based knowledge distillation, AFKD, method to create a more compact tracker, which adaptively mimics the behavior of the teacher model OR-Track according to the task's difficulty. This student model, dubbed OR-Track-D, retains much of OR-Track's performance while offering higher efficiency. Extensive experiments on multiple UAV tracking benchmarks affirm the effectiveness and versatility of our approach, positioning it as a SOTA solution in real-time UAV tracking. To begin, we describe two random masking operations used to simulate occlusion challenges, one from MAE, and our proposed method based on a spatial Cox process. Although the former allows the model to learn robust representations that are less sensitive to noise or missing information by randomly ignoring certain parts of the input data during training, it is less effective when used to simulate occlusion since each spatial position, in the sense of block size, is masked out with equal probability, especially in our situation where the target template generally contains background. To ensure that the target is masked out as expected with higher probabilities at a given masking ratio, thereby making the occlusion simulation more effective, we employ a finite Cox process to model this masking operation. The Cox process can be regarded as the result of a two-stage random mechanism, for which it is sometimes termed doubly stochastic Poisson process. The finite Cox processes can be simulated in a straightforward way, based on the hierarchical nature of the model. Specifically, in the first step, the intensity lambda, x, y, is generated, which is a bell-shaped function that gives more intensities to the central area. In the second step, an inhomogeneous Poisson point process is simulated using the generated lambda, x, y. The thinning algorithm is used here for simulating inhomogeneous Poisson point processes. It involves simulating a homogeneous Poisson point process with a higher rate than the maximum possible rate of the inhomogeneous process, and then thinning out the generated points to match the desired intensity function. Additionally, we propose adaptively transferring knowledge based on the difficulty of the tracking task. AFKD quantify this difficulty using the deviation of the GIOU loss from its average value, calculated between the student's prediction and the ground truth. Adapting knowledge transfer based on difficulty ensures that the student model doesn't heavily adjust its weights on easy tasks which it can handle already, probably due to its generalizability. Instead, it focuses more on challenging scenarios where its feature representation is less effective. For the choice of teacher-student architectures, we adopt a self-similar approach, where the student model mirrors the teacher's architecture, but employs a smaller VIT backbone, using fewer VIT blocks. This strategy simplifies the design and eliminates the need for additional alignment techniques that would otherwise be necessary due to mismatched feature dimensions. Extensive experiments on multiple benchmarks validate the effectiveness of our method, demonstrating its state-of-the-art performance. Compared to lightweight trackers, our OR-Track-DEIT achieves the highest average precision and average success of 85.6% and 65%, respectively, among all competing trackers. Although a BAVI track achieves performance close to our OR-Track-DEIT, its GPU speed is significantly lower, with a 23.6% relative gap. Notably, when the proposed adaptive knowledge distillation is applied to OR-Track-DEIT, the resulting student model, OR-Track-DEIT, shows a significant speed increase only by a minimal reduction in accuracy. Compared to SOTA deep trackers, our OR-Track-DEIT excel by achieving the fastest speed while maintaining high performance. On average, although trackers like ACUA-Track, HI-Track, and our OM-Track achieve precision comparable to our OR-Track-DEIT, their GPU speeds are much slower. Specifically, our method is 3.8 6.5, and 4.3 times faster than a QA track, HIP track, and our OM track, respectively. These results indicate that our method delivers both high precision and speed, validating its suitability for real-time UAV tracking that prioritizes efficiency as well as accuracy. To provide further insights into our proposed O or R, we present attention and feature maps produced by O or track DEIT, with and without occlusion-robust enhancement. We observe that O or track DEIT with OR maintains a clearer focus on the targets, and exhibits more consistent feature maps across masking ratios. These results support the effectiveness of our component. Thanks for your listening.